Thanks for tonight.
Oh yeah, but as long as it's recording, I think it's fine enough. Well, welcome. We'll start by going over the assignments from last time. So if you could read them out, if you have them in front of you, that would be great. Those assignments were set last time. Or do you have that one? You have that one. So I'll borrow this one here. We just need to practice a bit more on differentiating. So I gave some exercises last time. I see there are 20 exercises. I'll start going through them. And if it goes too fast, just stop me. In the first exercise, it says you need to differentiate the function x cubed times parentheses x plus 2. And here one might think to use the product rule because there are two functions multiplied together. But you don't need to at all because this function belongs to the same family. This is a first degree polynomial and it's a third degree polynomial. If we just multiply them together, we get a fourth degree polynomial, which we can differentiate directly. So without differentiating, just by using algebra, we get x to the fourth. This time it's d2x cubed. And so we can just differentiate what we see there. So if I substitute x to the fourth plus 2x cubed, so I better write it down like this, as I've written to my neighbors, I'm in the process of differentiating. And then I just differentiate piecewise. I differentiate that one on its own and that one on its own. And it's a power function, so you bring the exponent down in front and get 4x and raise one less exponent than before. Same here, the 2 stays, multiply by 3. That gives 6, and then x is raised to one less exponent than before. So this is the result. And that could also have been obtained by differentiating the first factor, multiplied by the second factor untouched, plus the first factor untouched, multiplied by the second factor differentiated. So I've used the product rule. Any questions on that? Exercise 2. So there's a raised to the x times the natural logarithm of x. And we need to differentiate this here. There's no way around it, because now it's two functions that aren't related in a way that you can reduce them. You can't reduce it, so it's its own thing, it's its own thing. And when I have to differentiate them, I'll use the product rule. So I differentiate the first factor and multiply by others. It's actually unpleasant. The e to the x is differentiated and gives itself. So now I've differentiated e to the x. You can't see that I have, but I have, because it gives itself. So you multiply by a factor untouched. There we go. Now I'm writing plus, well, do the reverse, first factor untouched. You can't see that it's untouched, but it is. It could just as well be differentiated because it explains itself, but it's untouched. And then you multiply by the second factor, differentiated. And ln of something differentiated gives 1 over something, so it gives 1 over x. And now I see that e to the power of x is present in both terms, in this term and that term. So this term is also called a product because there are two factors. But because it's present in both terms, you can factor e to the power of x out of the parentheses. E to the power of x should multiply an x from here. Then here x should be multiplied by an extra part. So therefore I can write the result. That was exercise 2. And that was clothes. It says e raised to the power of 7 something. Multiply the snooze by the axis. And we'll differentiate that. And again, I can't avoid using the product rule because e and 7x can cosinus to axion. They live their own lives. They can't be written more neatly than this. So you can't reduce it first with algebra. But that's always the first thing you try. Can I make it neater with algebra before I start differentiating or integrating or whatever it is you need to do? If I need to differentiate the first factor and multiply by the second factor untouched, plus the reverse afterwards, I realize that the first factor itself is a composite function. Because e is not just there in the equation, but in 7x, where 7x is a function in itself. So here you actually need to use the product rule first, but inside the product rule, you need to use the chain rule. So you need to use rules 3 and 5 within each other. So I start by differentiating e in 7x. That's straightforward. Because e to the 7x is differentiated with respect to 7x, it gives e to the 7x. But I'm not supposed to differentiate e to 7x with respect to 7x. I need to differentiate e to 7x with respect to x. So I need to remember to multiply by 7x itself, and that gives 7. So this here, this is e to the 7x differentiated with respect to x. That's e to the 7x differentiated with respect to 7x. So be careful with this. It's the composite rule. Then I have to multiply it by this untouched. That's cosine squared of t times x. Like that. Then I need to write a plus sign. because that's what products tell me to do. Then I need to take the first factor untouched, which must be e to the power of 7x. And then I multiply it by k cosine squared of x differentiated. But k cosine squared of x is also a composite function because x squared is inserted as the argument in the k cosine. So first, I think, what does k cosine of something differentiated give? It gives negative sine of that something. So I need to multiply by bracket of negative sine of that something, which is still x squared. So what is this? This is k cosine squared of x differentiated with respect to x squared. But I'm not supposed to differentiate with respect to x squared. I'm supposed to differentiate with respect to x. So I also need to remember to multiply x squared differentiated, and that results in 2x. And now I see e to the 7x as a common factor because it appears in both terms. So I can factor it out if I want to. It's not necessary, but it can make it look a bit nicer. What is left? There is 7x k cosine squared of x. And over here, there's minus 2x. Minus 2x sine of x squared. So minus 2x sine x to x squared. And then it's done. So that was exercise 3. Let's see if we can bring exercise 4 up here. And feel free to ask questions along the way if there's anything. Exercise 4, it says e to the minus x.
The times sign of 2x.
And we have to differentiate it, so I'm putting a big parenthesis around and writing mark, which means now I'm differentiating. So that mark means I'm differentiating with respect to x now. If you need another way to write it, you can actually write it like this. This is how it's typically written at university.
And there's a really good reason for doing it that way.
Here it says, now I want to differentiate with respect to x, that there. So let's try it. I'm differentiating ZA, that's the product rule. Since it's one function multiplied by another function. And then I realized that the two functions being multiplied are both composite functions. So again,
I need to use rule number 5.
From the chain rule.
Inside rule book 3, which was broken.
Differentiate the first factor and multiply by the second factor untouched. What does e to the something give with respect to that something? It gives itself, which means e to the something. So e to the minus x is differentiated to minus x. So what is this? It's e to the minus x differentiated with respect to minus x. But I shouldn't differentiate with respect to minus x. I should differentiate with respect to x. So I just need to remember to multiply by the inside differentiated, and minus x differentiated gives minus 1. So what is this now? This is e to the minus x differentiated with respect to x. That was big. It must then be multiplied by the other factor untouched. And that's what the product rule says. So I just multiply by sine of 2x. Then I write the plus, because that's what the product rule says I should do. Then I take the first factor untouched. So I just copy e to the minus x. And I multiply that now
by 2x differentiated with respect to x.
So what can I say?
Minus the 2x differentiated with respect to
Division to 2x gives cosine?
I don't think so. Sine differentiates to cosines.
But I wasn't supposed to differentiate with respect to 2x. I was supposed to differentiate with respect to x. So I just need to remember what twice differentiated gives. And what we can see now is that e to the minus x appears in both places. So it's a common factor, which we can factor out. And what we have left inside the parentheses is 2 times cosine. That's 2x. And I just decided to write that first, because it had a plus in front of it. And here, there's a minus, so I can make it look a bit nicer.
So this is my final
Congratulations.
result. That was task number 4.
Get ready to open. It says ln of sine of 2x.
And I want to differentiate all that.
So I'll put parentheses around the whole thing.
Now I'm
and
getting
then
ready.
I want to write d dex.
So now I want to differentiate it with respect to x.
So, yes,
Right?
Yep.
it says of sine of 2x. So it's a composite function. And it's not just simply composed. It's doubly composed because it's a function within another function. inside a third function. Can you see that? 2x is a function that's been put inside the sine function, and the sine function is a function placed inside the logarithm function. When you have to differentiate such a case, you start from the outside. And if you go far enough away and look at this, all you can see from a distance is that it says ln of something. So I just need to bring everything in to something. And that gives 1 over something. So ln of something differentiated with respect to something gives 1 over that something, and that something is sine of 2x. But I'm not finished, because now I get a bit closer to the board and I can see it says ln of sine. So I think, wait, I need to remember to multiply with the derivative of sine. And what does sine of something give when differentiated? It gives cosine of something, even the same something. Then I move even closer to the board and notice that it says down, 2x inside there. So I also need to differentiate 2x, which gives 2. And then I multiply with that 2, and then I'm done.
If you want, you could adjust the course.
So there's also up here. In the numerator, it says cos 2x over sin 2x. That's what you call the cotangent.
To 2x, and then also multiplying by 2.
You can write it like this if you want. Or you could just put 2 lines under here and just multiply up there in the numerator. The tangent is sine over cosine. The cotangent is cosine over sine.
Someone came up with this, so it's not something the committee will accept.
Yes, it is. Just tidy up the first one a bit. So we've reached problem 6, and it says sine to the power of e to the minus x. And we want to differentiate it, so now we're going to write it the high school way. Let's just mark it. I need to differentiate sine of something, and the only thing I can see from far away from the board is that there's a sine of something. And sine of something differentiated with respect to something gives cosine of that something itself.
So this gives cosine of that variable.
Then I get closer to the board and figure out what I was taking sine of. It's e to the minus x, and now I need to differentiate e to the minus x and multiply it in. And e to the minus x is itself a composite function, because minus x is inserted in place of x. So what does e to something differentiated with respect to something give? It gives e to something. E to what? The same something as before, of course. So I multiply by that variable differentiated because I got a bit closer to the board. And minus x differentiated gives minus 1. So I need to remember to multiply by minus 1. And then we have the result. Let's just put 2 lines here. Do you have any questions now?
Does that make sense? Great. Task 7.
It says cosine of ln of negative x. So I really enjoyed working with composite functions, I can see, when I wrote this.
And we need to differentiate this.
It's
So we put
parentheses around the whole sentence.
Diltog and write a label. Remember, you need to
write it down. That you have to tell the reader that you're differentiating. So you must
just
not
write it without the label and then write equals. So you can't see it's being differentiated.
So we'll start that cross.
If it's fronted, then it's negative.
See more.
And now we have to go to the basement.
Minus sine of the natural log of minus x. Then I know it's the natural log, so I better multiply by the natural log of something derived. That gives 1 over something. And then finally, I just have to deal with x, which gives 1. So minus cancels with minus, and we end up with a single minus. So what do I get? I get minus sine of the natural log of minus x over x. And then we're done. I just multiply the numerator, right? What? And if you multiply by minus 1, but also divide by minus 1, they cancel each other out. So the 2 minuses ate each other, leaving only the minus that was out there. And of course, the minus goes into the
There's a
decision.
document for LND too, yes.
That was task 7.
If there are no more questions, then I'll erase the board.
Oh, that's good. That's 1,000. Did I take it? Permanent. It's awful when you've used a real marker, Tusio.
It's awful enough when you've written that you're ordinary, I see.
What you're seeing now is why I like chalkboards. Okay. You can just take a break while I erase this. Every time I wipe a board like this, I wonder if anyone loves whiteboards. Especially those who write a lot when they teach. You get that far? Okay, good. That was big.
2, raise 3 eggs.
And I'd like to differentiate that.
Where exactly do you do that?
Oh, right. There was something about 2.
xnet is differentiated.
Almost by itself. It gave 2 times ln of 2 in the xnet. So 2 to the power of 3 xnet differentiated. That should also be itself.
If I just remember to multiply by ln of 2.
But then I also need to remember that 3x is a function. So I also need to differentiate 3x, which gives 3. So here is the answer. Because it's a composite function, because 3x is a function that jumped into the x's place in the exponential function of 2 to the x and gave 9. There's the square root of a x cubed plus 4x.
So we think the square root is something
Differentiated, that's 1 over 2 squares and something.
So let's put a big parenthesis and write them. We are differentiating now. So that gives 1 over 2 times the square root of the same thing as before, x cubed plus 4x.
But then we realize this is also a
So
function.
let's just write differentiate times.
This differentiation gives 3x cubed.
So I need to remember to multiply by parentheses 3x squared plus 4. And the parenthesis is important at the start.
Because here I only get to multiply by 3x. But if I then multiply 3x squared plus 4 up in the numerator, it
And
becomes
then you can see it'll look like this. 3x squared plus 4. All that divided by 2 times the square we do.
of x cubed. So 4x.
And then it's done.
Task 10, and then we're halfway.
It says there cosine of x.
Times Euler's number raised to the power of 5x. So I need to finish the product rule. I differentiate the first factor. Derivative of cosine gives minus sine, which I multiply by the second factor untouched, which is e to the power of 5x. Then I write a plus, because the product rule says I should. Then I leave the first factor untouched, which is cosine of x. And then I differentiate e to the power of 5x, but it first gives itself e to the power of 5x. Normally, I must remember to multiply by 5 because it's a combined function. I see e to the power of 5x is a common factor, so I can write it more nicely as e raised to the power of 5x times cosine. There's a cosine 6 times 5.
Minus sine of x.
You've experienced 10. Here it says the natural logarithm of the square root of sine of x. The natural log
Of the square root of sine of x.
and all of that. I need to differentiate. Okay, so we say the natural log of something differentiated is 1 over that something. 1 over what?
Same command as before.
So 1 over square.
Above sine of x.
But then I need to start with the square round and something.
That's in the future.
But that gives 1 over 2.
Multiply it. That's something. So it gives 1 over 2 squared sine.
What happened
Are you
then?
working on
It
this
was in
established?
frontier?
Here, cosinus. And then I'm done. You multiply 2 brewers every time. Denominator with denominator, square output, they cancel out. So there's just a bottom sign here, right? So the square root is x times the square root of x. That's equal to x.
So the square is sine, the square is sine, it must be sine. Are you following that?
Do you have any questions? So this is actually correct.
You can just write it a
nicer
little
if you want, because you can multiply the cosine into the numerator.
and up in the numerator.
One,
There's
because you
1 times
multiply
2
two.
fractions each time.
Top with top, bottom with bottom.
And then I have to multiply square and sine with square and sine, but that just gives sine.
So it's going to look like this. And this is the same as 1/2 times cotangent to x, because cosine and sine have been named cotangent. So there you can place two straps, and basically you can also place two straps up. That's also correct. The difference here is whether you can reduce.
Right now, we're mostly focused on differentiating.
Any questions otherwise? Exercise 12.
N of cosine to the power of 3.
All of that will be fronted.
Now we can do it soon, right? We start with the ln differentiated of 1 over something, multiplied by that something to the ln differentiated. So I get 1 over cos to the power of x cubed, multiplied by the cosine differentiated, which gives minus sin to the power of x cubed, multiplied by x cubed differentiated, which gives 30x squared. Then we're done.
It can be reduced a bit neatly. I would multiply that up there.
Now we've subtracted. There's 1/2 x plus 2, all in parentheses. And that's what we will differentiate. So it's a composite function. It basically just says something in the 8th power. Differentiate that 8 times, it's something to the 7th power. So you start from the outside, just think, I'll multiply by 8 in front and subtract 1 from the power. Then I get 8 times half x plus 2, all to the 7th power. But I'm not finished, because I need to differentiate the inside, and half x plus 2 differentiated gives half. Because it's a straight line
With a slope like this.
and half times 8 gives 4. So I can write it as 4 times half x plus 2. The whole thing to the 7th power. And that was problem 13.
Now there's going to be a bad sound.
I'll show the board again.
It's been tried. Is it okay if I erase? Should I start over here?
I'll stop it being split here. Relax, you have plenty of time before I get down here. Are you dodging my question? No. Okay.
Then it starts running.
Yes, the system there. You have to figure out the system, that's right. Can I finish?
Just start from when it's assembled by you. And then you simply have to put on glasses where you're blind to all details. You can only see the big picture. Is it a fraction? Fraction rule? Is it a product? Product rule? Once you get started, it might be that you'll need other rules within those rules. For example, if there are composite functions involved in a product, then you need to use composite rules within the product rule. Number 14. There it says xen plus 3x minus 2. All the elevated in minus first, and it's happening now from a clear point. What does it say? Something in minus first differentiated. Well, that's just multiplying the exponent down and subtracting 1 from the exponent. So that gives minus x squared plus 3x minus 2. And here it actually says minus 1, but I didn't feel like writing it. I'll just write minus. And then I need to raise one exponent, which is one less, but it has to be -2. But I'm not done because this is a composite function. So I must remember to multiply with the derivative of the inside, and it'll be 2x plus 3. Because x squared differentiated becomes 2x, 3 and x differentiated becomes 3. -2 differentiated gives 0. As it's a constant on its own, it disappears. So that's the answer. The walk of color is in the fjord. Now we're getting tired of this, so I should hurry up a bit, right? Exit 30 minutes.
2x.
That's the fun part about raising to a power.
Step -5.
Here I see that I thought they should know it also applies even when the exponent is negative. So what do? We start with something to the -5th. That's -5 times something to the -6th. So I say -5 times the same something as before, which was x cubed minus 7x. Raise that exponent to 1 less than -5. So it's -6. Multiply together
It's
with that.
fronted, and that gives 3x squared.
-7. And then we're done. So we're up at 50 minutes. And then we make it 16.
Here, I figured out 2x plus 3, all raised to the power of 1/2.
So that was another way to write the square root. Here it just says square roots. But you can also solve it just by thinking that I multiply down by a half in front and subtract 1 from a half. So it results in 1/2 times the same thing as before, which was 2x plus 3. There's 1 less than a half. It must be -1/2. If I have a half and eat the whole, then I owe a half. And then I have to multiply by the inside differentiated, and that gives 2. And 2 cancels out with a half.
So what's written there in the middle is the result.
That was exercise 16. It's still raised to something in the 90s. It just totally goes away by multiplying by a half.
So number 17. And as I'm forced to my knees, it says x times the square root of x plus 3.
And I have to differentiate this here.
So I have to use the product rule because it's a product of two functions. So I'll start by taking that to the front. That gives a 1. Then I multiply it with that untouched one. Then I write the plus and do the opposite. Leave the first factor untouched, that's x. And then I have to differentiate that one. But that gives 1/2 square roots, the same as before. And finally, yeah, I have to differentiate the inner part, but that just gives a 1. So in principle, I should write x1, but I won't bother. Because x1 is the most neutral thing you can do. It's equivalent to doing absolutely nothing. In fact, 1 is called the neutral operator under multiplication. We'll see this with complex numbers too. There are also neutral complex numbers.
So that was the answer to this problem.
Here comes the, now I have to add it.
Are there any questions about this? Over here? Yeah, I don't need to write that either.
So I started to write it, then I felt bad, so it sounded bad.
Then we tackle problem 18. Yes, absolutely. Let's think it over again. You differentiate the first factor, which gives a 1, as I wrote, then erased. Then you multiply by the second factor unchanged, which is there, plus the first factor unchanged, which is there. Then multiply this part, where the square root is something differentiated, resulting in 1/2 times the square root of the same something as before. And finally, you multiply by that something differentiated, but it really gives 1. So technically, you should also multiply by 1. You need to see what you have in mind, okay? So we're almost there. Exercise 18, it says x cubed times the cosine of x cubed. And we have to differentiate that, so we have to use the product rule. So I differentiate the first factor first. That gives 3x squared. Multiply by the second factor unchanged, cosine of x cubed,
plus the first factor unchanged, x cubed.
The one that differentiates, but that gives minus, so I need to change my plus to a minus. But it's a composite function, so I need to also start differentiating x to the third.
Very good.
No, don't look. No.
And then we're done.
And if you want, I see, you can factor out 3x squared, but let's just leave it there. Yeah, that's just as fine. Truth-wise, it's just as fine. Aesthetically speaking, it is.
Thank you for today.
Yes. So, there are a few minutes.
There's nothing at
And
all.
I just need to remind you that I have to remember to register your.
I just thought of that. I always forget. X to the fifth times in it to x to the negative first. So all of these I need to differentiate. And it's not a variable. It's a symbol I'm differentiating. So I differentiate the first factor, which gives 5x to the fourth, times the second factor, untouched, which is signed to x to the negative first, like that. Then I write a plus, because the product rule says we must do that. Then I differentiate the first. Wait, no, I haven't done that, so I'll leave the first factor untouched, x to the fifth. And then I differentiate sin of something, which gives cosine to that something, even when it's the same something. So x to the negative first, copy paste that down there. And finally, remember to differentiate x to the negative first, which gives negative x to the negative second, because I multiply by negative 1 in front and subtract 1 from the exponent. Yeah, we'll just put 2 racks here. So that was the task for tonight.
Task 20, the final task.
X in position, over. Course text in Minders first. From a distance, we just see that it's a fraction. So we need to differentiate this entire fraction, and we'll use the fraction rule. And it was difficult to grasp intuitively, because why does the fraction rule look like it does? The fraction rule looks like this. Take two functions and divide them, then differentiate by doing the following. Differentiate the numerator and multiply by the denominator as is, minus, leave the numerator as is, and multiply by the differentiated denominator, and divide everything by the square of the denominator. Why did it look like that originally? That's because we're measuring how quickly the fraction changes if you tweak the numerators and denominators. If you adjust the numerators without changing the denominators, the fraction grows if the numerators grow. So it measures how fast do the numerators grow times the unchanged denominators, which is divided by the square of the denominators. This shows how quickly the fraction changes when I change the numerators without changing the denominators. Why is there a minus? Because if you make the denominators larger, the value of the fraction decreases if you don't touch the numerators. That's why there's a minus. The reason we divide by that is because the fraction is quite sensitive to how big the denominators are generally. You can probably imagine that if you have a fraction with a very small denominator, you barely need to adjust it before the fraction changes widely. But if you have a fraction where the denominators are huge, you can adjust the denominators a lot without changing the fraction. Think about it. A billionth, then say a billionth plus 1,000. It's almost the same as before. So even though I've adjusted the denominator by 1,000, the fraction has barely changed. That's why I've paused the changes.
So that's the rule. We need to differentiate the numerator first.
That gives 8 times 7. Then I multiply it with the denominator untouched, which is cosine of x to the first. Now I'm ready to start here. So I write the minus there. Minus, I can leave the numerator untouched, not 14th. And then I need to differentiate cosine of x to the minus first power. But the derivative of cosine is minus sine.
So I'm going to use sines, but I think I'll just write times sines.
And I do that because I also need to remember to multiply by x to the minus first differentiated, which gives minus x to the minus second. So just two negatives cancel each other out. I don't have room to write times x to the minus second there.
So I probably need to admit that. I should write a bit smaller and write it again.
Small boards aren't all that great either. So the numerator is untouched. Oh. Multiply the denominator. Oops, sorry. Differentiate the numerator. 8x to the 7th. Multiply the untouched denominator by the cosine of x to the negative first. Minus, because there's a minus sign in the circle. X in order is untouched. Multiply cosine differentiated, which gives minus sign, but I'll just write sign. I'm not writing minus sign
And the reason I'm not doing it is because I thought a step ahead and I needed to multiply by minus x to the negative second. So I'll just multiply by x to the negative second. So the minus cancels out and takes this minus with it. And then I need to divide everything by the untouched denominator. Square it. And then I'm done. And that was the result for the last one.
Does anyone have any questions about this now?
I'll move so you can see the board. So how many here feel they've gotten better at differentiating by going through this? Well, that's good. So now it's gotten worse, I mean.
Okay, now we understand. That's good, because now we're also going to learn integration, and it's hopeless if you can't differentiate. Absolutely hopeless. And it's even more hopeless to understand differential equations if you can simplify them, which you can't do if you can't differentiate. And it's hard to differentiate if you don't know algebra, so you can't simplify. So again, the story starts with when you're sitting at home, thinking you've gotten better. Start by checking if you've gotten better at algebra. Just basic fractions, simplify common denominators, and make it neat. That's the first and most important thing. And when people write to me today, those who are studying for an engineering degree and have solved some problem, it's 99% of the time algebra they can't remember. Isn't that crazy? They've finished with it, they've gotten top grades in math. Now they're in the next engineering program, but they still can't simplify fractions. So you can never be good enough at algebra. You get close to never being able to improve in algebra. That never happens. I can feel that I'm constantly getting better at it myself. When I was writing my thesis at D2 for the engineering program, I realized when I saw my advisor, who was a physics professor, that I still wasn't good enough at algebra, because he could hold things in his head that I couldn't even keep track of with paper and pencil. So you can keep getting better at it. And that's what's so great about math. You keep getting better the longer you do it, and you never reach the finish line. You can become infinitely good. It would be awesome if someday there are aliens who have become infinitely good at math. I kind of secretly hope that they suddenly land in my backyard and I can ask them a bunch of math questions. Let's go ahead and start some integration before we take the break. Or should we take the break now? No, not yet. All right. So now the headline is integrated. And the first thing that I want to tell you, it's something that amazed me, that I never understood before. I didn't get it the first time I encountered it. When you see it like this, it means some things. And what I didn't realize until much later in my studies was that it actually says, would you be kind and nice and friendly? It's asking, would you be kind and nice and friendly and find all functions if you differentiate them with respect to x gifs? That's what it says. It's just been boiled down to math language. So it looks a bit neat like that. But that's what it actually means. So the answer is this. So listen to the question again. Would you be kind and nice and write down all functions that, if you differentiate them with respect to x, result in little f(x)? And what are the functions that, when differentiated, give little f(x)? Those are all the primitive functions, as they are called. Big F is the name of a function that, when differentiated, gives little f. Why does it say plus k? Well, it's because any constant that might be added disappears when you differentiate. So here are all the answers to that question. That's what it's called. The indefinite integral. So here's an example. We'll start with, please be kind and wait in the sign. And then we write 2x takes. So what does it say? It says, please be kind and wait and find all functions that, if you differentiate them with respect to x, give you 2x. So I just need to think, can I think of one that when differentiated gives 2x when I have x squared? So I just write x squared, and I think, so they must all be here. Because x squared differentiated gives 2x, but x squared plus 7 differentiated also gives 2x. So x squared plus anything, if you differentiate it, you get 2x. And the reason you write plus k is because otherwise you haven't answered the question. Because the question was, and remember it, please be kind, and find all functions that, when differentiated with respect to x, give you 2x. So that k can be anything. So you write it like this. K can be an element of R, meaning k is any real number you can think of. All numbers work. Example 2. Let's see if we can find all functions that, when differentiated, give x squared. So again, it says here, would you be kind and find all functions that, when you differentiate them with respect to x, give x squared? And yes, what's written there, right after the integral sign, but before the symbol dx, is called the integrand. And that guy, that's our integrand. And it's probably better if I write it up here and point to it, because up here it's written generally. So this is my integrand. Can we find a function that, when differentiated, ends up being x squared? Well, it must be something with x cubed, right? Why? Because we know that when you differentiate x cubed, you subtract 1 from the exponent. The problem is, when I differentiate x cubed, I don't get x squared, I get 3x squared. So you fix it like this. You just stick a 1/3 in front, and that fixes it. And then you need to remember to say plus c. Where c is an element of the reals, then you have all the answers. So this is the answer. So you say you found the indefinite integral now. Let's take example 3. Let's say we need to find the integral of x to some power. It's x. So it says, can't you just be nice and find all functions if you differentiate them with respect to x? Here the integral x in int. Well, we can almost guess it, because there must be something with x raised to more than the 40th power. Because we know that when you differentiate, 1 gets subtracted. So when you integrate, 1 gets added. The problem is just that if I differentiate x to the power of n plus 1, it sure doesn't give n and x to the power of n. It doesn't, but it's added on. Because if I differentiate x to the power of n plus 1, it gives n plus 1 times it in front, times x raised to the power of n plus 1. And that n plus 1 in front here isn't in my integrand. That's what I want. It's not here, so I get rid of it like this. I just multiply 1 over n plus 1 beforehand. So that solves the problem. Now, if I differentiate this, what do you get? 1 over n plus 1 times x to the power, n plus 1 differentiated. Then I multiply n plus 1 down on the fraction in the numerator, so it cancels out with n plus 1. And then I subtract 1, and I land on x to the nth. The numbers add up. And of course, we must remember our k. If you have to mention it, for the monthly exam, you can call it an arbitrary integration constant, and then you sound smart. Add 2 for the 1.
It is added. Work trigonometry because it is dangerous.
Advice to say random and integration constant, because it's one that appears when integrating. There's madness with a method.
But there's a lot of madness in all academic subjects.
It's because all academics try to say what they know in the most complex way possible to justify more than 1,000 crowns per hour. That's how the world is. But it just means that remember to write plus k. Otherwise, you haven't answered the question.
If one knew how simple a thing my cover is, that's what tasted.
Why am I answering insanely? Example 4. What should we take then? What is it again if it says the integral of 5x squared? We can take advantage of the fact that we already have the solution if it doesn't say 5. Because here, all you need to do is this. You simply pull that 5 out of the integral. Think about it this way. If I need to integrate 5x squared, I might as well integrate x squared and just remember to multiply by 5 at the end. For the constants that you multiply, they stay when you integrate. exactly as they stay when you differentiate. And we already know that integral, it gave us this. So therefore, it must give 5 times 1/3 of x cubed. And then plus k. Now, some might ask, why don't you write 5k? Because wouldn't 5 be multiplied by that and that? Yes, that's right. But 5 times a constant is also a constant. So there's no reason to mess up that constant with a 5, because the constant can already be anything. So you don't bother to write 5k, you just write k. So this is the answer, and you can go ahead and multiply the 5 on top. So it says 5/3. So you'll write that 5/3 x cubed plus k, finished. So these were some examples of what it means to compute an indefinite integral. And if there are no questions, I'll just erase the board and write up some rules for indefinite integrals. Then we can try practicing slightly more complex integration. And it won't be long before we take a break. I can see just by looking in your eyes, it's needed. So in about 10 minutes, we'll have a break. Any questions? Nope. No. Just like there are rules for differentiation, there are rules for integrating indefinite integrals. And you can pretty much guess that if there are indefinite integrals, then there are also definite integrals, which we'll cover afterwards.
So here are the rules.
And then I'll show some examples of where we use them. And we'll take a break, and then I'll put up a lot of exercises so you can hear them, and I'll go around helping. So the rules look like this. Rule number 1, if you encounter an integral where there's a constant multiplied with the integrand, or more precisely, if your integrand contains a constant that's multiplied like that, then you can simply move that constant outside the integral sign, just like we did with the number 5. And why is that true? Can it be proven? It's very simple that it is true. Yes, you can, but to prove it, you first need to understand the following.
What does that mean?
When I say the integral of 2x dx equals x squared plus k, what does that actually mean? This means that the equality is true if, and only if, differentiating over there gives the integral. So this equality is true. Why is it true? Because if I differentiate with respect to x, that's the x plus k. Well, what do I get then? The differentiation gives me 2x. A constant that stands alone differentiates to 0. So I get 2x. And what is 2x? That's my integrand. What is the original integral?
That's why the equality is true. Are you following this?
The equality is true because differentiating gives back the integrand. Why is the reality check so true, if it is true?
It is true because it is differentiated, giving it that.
That's how you prove it. So I can just prove the rules quickly.
Let's try and see here.
If I differentiate with respect to x, get times the integral of f.
dx, what do I get then?
Well, a constant multiplied by it stays.
Standing, when you differentiate, it stays put. And when I differentiate something that needs to be integrated, the two operations cancel each other out because they are inverses. That means when I ddx something that's integrated, the ddx consumes the ddx and the integral sign. So that's the only thing that survives.
It's fake.
So it gives k times fx, and then it's proven. So now we've proven that that rule is correct. Calculus rule number 2. If you need to integrate two functions that are either added or subtracted, like this, then you integrate term by term. This means you just split it into two integrals, so it becomes the integral of f. And if it was a plus,
When there's a plus,
you
then
write
we
a
write a
plus.
plus.
And if it was a minus,
When there's a minus,
you write a minus.
You write the minus, and then you get the integral.
Are you ready?
So that's calculus rule number 2. And that means, as an example,
Then I could say,
we are revenue.
what's up? There's never 2x plus x squared.
Just notice one thing here. There are many mathematicians who don't write this bracket that I've written here, but you should do it.
but some have become so sloppy that they've stopped doing it.
And why should you write a bracket around the integrand? It's because when you're a physicist, you know that this means take a little bit of and
X
multiply it at the
motion
point.
here.
Since this means a small bit of x that needs to be multiplied by that function, it has to be multiplied on both sides, and it won't be unless you put a parenthesis. So it's basically wrong if there's no parenthesis. So remember to put parentheses in the integrand if there are multiple terms. And what we need to do now is split it into 2 integrals, giving us the integral of 2 times x plus the integral of x squared dx. And now we can solve it by solving each one separately. The antiderivative of 2x, what is it? It's x squared plus c, but I don't need to write plus c. Just remember to do it for one of them, because c plus c is a new c, right? The antiderivative of x squared was 1/3 x cubed plus another c. So it's not weird that you don't need to write the c for both integrals, because it's kind of a double conflict. You just need to remember some additive arbitrary constant of integration. You do that for all answers to that question. Why is an equality sign true? Can we prove it? Yes, you just take everything over there and differentiate it. It's super easy. You can do it in your head. How do you differentiate a sum or a difference? Term by term. And when I differentiate the first integral, I get the first integrand. And when I differentiate the second integral, I get the second integrand. So it ends up as f of x plus or minus g of x. And that's exactly my
So
integrand.
it's proven.
Exercise number 3. Sorry for the next kitchen. It looks like this. If you ever need to integrate it one day,
2 functions.
multiplied by each other. So what you do is decide to just scan the integral, and then you discover which of the 2 functions becomes nicer when differentiated. Why consider which of the 2 becomes nicer when differentiated?
Nicer when differentiated, but I have to integrate.
You'll see now in the rule, because the rule says that you need to take an antiderivative of one of them and multiply it by the other one untouched, minus a new integral. The antiderivative of the same map, multiply the other map differentiated. And here's the hint for why you should check which one becomes prettier when differentiated. Because when you solve this integral, a new integral appears. And if g becomes uglier when differentiated, you risk that the new integral is harder to solve than it was originally. And that's a bit tricky. Imagine a rule you use, and every time you use it, you get a new problem that's harder than the one you started with. It's better with rules where the integral you also have to solve is easier than the one you started with. The other thing is a miss. You'll never get it solved. The problem just explodes, and it gets worse and worse. First, I want to give an example of this rule, when to use it, and then I'll prove it, because it's not obviously true. So here's an example, example number 3. Let's say we need to find the integral of x times Euler's number raised to the x. And now I ask you, does x become simpler when differentiated? Or does the Euler's number term become simpler when differentiated? Here, simpler means easier to integrate. Differentiating Euler's number raised to the x, what does that give? Is it simpler after differentiation? It's exactly the same. So it's not simpler. It's already a bit complicated, but it needs to become simpler. I ask you, does one of these 2 functions become simpler when differentiated? Well, it's definitely not Euler's number term. It stays the same according to this
It's
principle.
just as nice as it always has been.
So it must be x, right? If you differentiate x, you get 1.
And 1 is much simpler than an 1.
No, it isn't. Why? Because it's much easier to integrate.
And therefore, because it's that one which becomes pretty, and I've been differentiated,
And because in the rain rule, it's the name g that's differentiated, you can see that this one I should call g, and this one I should call f. And I have to decide on that naming before I start using the rule, you see. Because there are two functions multiplied with each other. Do it like this, but then I need to know which one I'm calling f and which one I'm calling g. You know, it needs to be decided. And I'm telling you beforehand, the smart thing is to decide that the one that becomes pretty and I get differentiated is the one you call g. How do I know that? Because I've tried the other way and it doesn't work. So it's purely from experience. Soon you'll know it too when you've tried it. Okay? So let's try it now. So what does the rule say? Find the antiderivative of f. That's the first thing I need to do. What's the antiderivative of e in x terms? It's easy. Fortunately, it's itself, she said now. Multiplied by the other one untouched. That's what it says. Multiplied by g. And the other one? Well, that was x, right? So it's multiplied by x. Then write a minus. Why? Because the rule says so. But are we just learning to obey the subject? Yes, until further. First, we become trained hands, and later, we'll understand why. So we write the minus, because the rule dictates. And then, I write a new integral sign. And then I write again f, because it's again f. So it's again e to the x.
Jew. That would have been applicable. And
Then I have to multiply it by g prime, but that just gives a 1. So this is big F, and this here is g prime, and then I have to remember to write the symbol dx. Just a quick note, you can never write an integral sign without also adding the symbol dx. They belong together as notation. No integrals without dx, dis, this, or tis. There must be a d something. Usually it's dipole, but there has to be something. It's here. So you can't have an integral sign without a d something. And there's always someone asking me, what happens to dx when I solve it? That question doesn't make sense. Listen up. If I ask you guys, what's your name? You're not answering. What's your name, John? You only answer John. Okay. So when I ask like this, find me all the functions that differentiate gear x. What's the answer? It's 1/2 x squared plus k. So someone asks, what happens to dx? It disappeared because dx was part of the question, and you don't read the question aloud again when you answer. Here it says, would you be so kind and nice and find all the functions differentiated with respect to x dx? Yes, 1/2 x to the n plus k. You don't need to write anything about dx over here. Dex was part of the way mathematicians wrote questions.
All right, let's just finish calculating this. I can't do more about that, so it's copy paste when I see EEX this.
Multiply x minus, and then I need to inscribe EX times 1. But EX times 1 is just EX itself, and the antiderivative of EX is thankfully easy. It's just EX, and then write plus. The constant, is it just as strong? Thank you, especially. If it is, then you should be able to differentiate this and get to it. And that's the last
To the green pauser. We'll just test it. But normally one doesn't do it. It's just to be nice. We're trying it to see if it fits. So now I'd like to try
differentiate my answer standing here to see if it gives what it should.
I'll just drop the constant because I already know it when they're
It
finished.
disappears anyway. So the interesting thing is what happens when they differentiate this, if they really give that. So let's try. I'm differentiating a product. So I need to differentiate the first factor times the second factor untouched. That gives the EX times X.
Plus the reverse. First factor untouched.
Times the second factor differentiated.
Now I'll differentiate this on its own because it's another term. So I write a minus and differentiate e to the power of x. But that's straightforward. E to the power of x times 1 gives e to the power of x, which is cancelled by minus e to the power of x. So the whole thing gives e to the power of x times x. But since the order of the factors doesn't matter, it's the same as x times a to the power of x. So that's pretty cool. That makes just as much sense. Let's take a 10-minute break and then we'll start again. If you need to convince yourself that the rule is correct, then the last one we looked at, rule 3, said that the integral is a function f times another function g.
It says to integrate the function of one of them and multiply it by the other untouched. Minus a new integral sign, where you take the antiderivative again of the same function you chose before and multiply it with g differentiated. If you now need to believe that the rule is correct, and it wasn't just a miracle that it worked before. In other words, if I have to prove that it's true.
So what do I do then?
We exploit to prove that. If you differentiate something that is already integrated, if you differentiate something that is already integrated, the differentiation operation cancels the integration operation, and you just get the derivative. So here's an unusually ugly method, and write the function notation on it.
Congratulations.
You shouldn't do that anyway. So remember, if you differentiate something that is already integrated with respect to the same variable, that means if it says die there, but dx there, it doesn't work. It has to be with respect to the same variable. Then the two operations cancel each other out, and you just get what's under the integral sign. And I can use that, because if that equality sign holds true, then it must be that if I differentiate all this stuff here, it should just refer to this product here. So we can prove it like this. Proof. I'm differentiating now with respect to x, all of this here. So I'm just doing Ctrl-C, Ctrl-V. I'm pasting it down here.
So I'm copying after myself.
And here we are. So let's see if we can figure out if they are from a file.
Watch yourselves, Ed.
It's in here.
Well, if I may differentiate it first,
It's just here.
then I'll write that I need to differentiate this.
Minus and set.
Because I need to do it term by term.
And this is a term, and this is a term, because terms are things that exist.
Separation is either plus or minus. And this is what I need for the exercise. Position yourself for your first factor and multiply by the second factor.
Enjoy.
I'll give a big
In the
after.
frontier.
Lowercase f. History is the name of a function that, when differentiated, gives lowercase f as an antiderivative.
Congratulations.
So now I'm on it. The one that's differentiated.
Times the one that's untouched, it says here.
So I write a plus, because the rule says so. Rome's rule 3 for differentiation says to write a plus, so I do that. Then I take the one that's untouched. I multiply by the one that's differentiated, because the rule says you should. Differentiation calculation.
So now I've differentiated that, so I'll write a minus.
And now I need to differentiate that there. But here I can use what's written up here. If I differentiate something that's already been integrated, it just gives the content under the integral error. So when I differentiate this, it just gives big F. Times mark. And now something happens that's pure magic. Swing. It ends up the same, but with opposite sign.
So the only thing left is that they're...
And the thing I'm happy about is that it gives that, because it was up to the limit. And that's why I've now proven that the equality sign must be true. Was that okay? So here comes the last rule of calculus, and it's the one most struggled with in high school, or the entrance course, or wherever they've battled with math. It's called integration by substitution. So now I'm going to slow down a bit.
And afterwards, we'll solve some problems.
I probably need the space, so I'll just empty it here. You're welcome. Hey, shouldn't we give it to Vilde? So the last rule of arithmetic, we could call it the Roma theorem number 4 for integration.
It's called the integral of.
If one day you encounter an integral with a function f of another function g
Looks nice.
under the integral sign, that's what we call a composite function. And if you're so lucky that it just multiplies to change the function's name.
That's the frontier.
Then the integral is usually quite simple.
if you're lucky enough that it has
needs
this
to have
manual right
structure.
here. The only thing you really need to do is find an antiderivative of f and let it act on g untouched. So the only thing you really need to do is find an antiderivative of f and let it act on g untouched. And can I prove that it's true? Because if this over here differentiated gives the integrand, then it's equivalently true. So let's just start by proving it. Oh, you've made my day, Christ. Thanks. So to prove it, I just go ahead and differentiate the right side and see if it turns into the boundary, which is the bandit standing after the integral sign, but before the symbol dx. So yes, d dx is exactly that one. How do I differentiate a composite function? Well, I start by differentiating the outer with respect to the inner, and capital F differentiated gives little f. So this must give little f, acting on g untouched. But I'm not done, because it's a composite function. I must remember to multiply by g differentiated, which just gives g prime. I can't write it differently, because it's calculus now. And then I see that what's written there, it's 100% identical to that, so it's just as transparent. So now we just need to learn to use the rule. Let me now show a couple of examples that are super easy, where you can scan and see the answer. And then let me take some that are a bit harder, where you need to be a bit sneakier to see the answer. You've got to learn creative accounting to see the answer. So here comes example 1. Example 1 related to calculation rule 4. So you can see that my example numbering has restarted. So let's take an example called
1 second.
the shell of
2x squared times 2x.
Dix.
So the first thing my eyes do is they do this and scan. They just scan the tasks. Where what? Where family? Which family? Family. Differentiation research. I wonder if there's a function here somewhere that, if I differentiate it,
GNM function.
will also be represented.
xcn is related to 2x.
Where does the family consist? X squared. If you differentiate it, you get 2x. Look up here. Look for a function g. That, if you differentiate it, gives g prime, which is also present.
If you see it, you can use this rule here.
So there should be a function that acts on another, and if you differentiate the one it acts on, it should also be there. That's when I first scan and realize that it's correct. It's there. So who is f and who is g? Well, then that inside must be g, and sine must be f, and this must be g. Can you see it? And according to the rule, what should I do? I just need to find capital F's, since it acts on g.
That was easy. I need to find an antiderivative for sin.
If you don't remember it, you should draw one of the circles. Do you remember? Here was cos, here was sine, here was cos, here was sine. So I'll just write it in cos, sine, minus sine, and minus k. And I need to integrate, so I should go that way. Because if you differentiate, it's really easy to run the clock the right way, but now we're going backwards. So it's this way. And I need to integrate sine, so I start with sine, and then integrate in the middle, which gives minus cosine. So it gives minus cosine to what? To k tilde, but who was g? I can't say anything else, and then I'm done.
Ta-da, now I have the example.
Example 2. The integral is cosine. Multiply 3x again. Captioned by Nikolai Winter. So I'm scanning. Is there family? Yes. Where x cubed, if you differentiate it, you get 3x squared. So this must be g. That must be g prime. And this must be f. And what does the rule say I should do? Attach an antiderivative to f and let it apply to g without tilde. See? Attach an antiderivative to f and let it apply to g without tilde. So let's do that. So I find the antiderivative of cosine, and it works over here. The cosine, and then I'm coming backward, then the sine. So it shouldn't go into sine. To the core there. unmoved, plus our constant.
That's the point. Well,
For example. No, I can't read this yet.
integrated.
Sine
To the x times x cover.
Are there any families?
because if you think
Yeah.
about
Yes,
it,
you are
married, then you become married. So this is gay. That's really weird. And that's what it is. So now I need to find the antiderivative of sin. It was minus cosine.
So this must be minus cosine of what?
Of x.
Because it should be the antiderivative working on g untouched.
Can it ever get harder? Yes, it can be a bit. So let's just take a known example. The integral of sine for x, John,
Times 6.
Do you have questions? Then we have the question afterwards. Okay, so this task, then it's scanned. Is there family? Well, x squared differentiated gives about 6x. More precisely, it gives 2x, but 6x is pretty close to being the same as 2x. Write on this factor. 3. If there's almost family, it also works. But you need to understand the word almost. Almost means that the family should be at most, except for a constant, which you just multiply by and fix. There mustn't be any extras.
It's needed to fix it. Or say it now, so now just fix it.
The idea is external.
It shouldn't be there. There must be just a constant multiplied that is wrong. Then it can be fixed.
Look here. I can actually do a clever rewrite of this. It actually says the integral of sine squared of x times 2 x times 3. Because 2x times 3 gives 6x. Are there any relatives? Yes. X squared differentiated gives 2x. And then there's that annoying 3. But that 3 isn't so annoying. It can just be taken outside the integral.
So I'll just take my 3 outside the integral in.
And then I have a pure delight, integral left, which is sine squared of x times 2 x dx. And that integral, I've solved it. It's right here. So I don't want to think again. I'll just grab the answer and put it in there.
So the answer must be 3 times that.
Minus cosine of. Excellent. And k? There's no need to keep going with 3, right? So I'll just write k on its own. So that's the answer. If you're not quite that creative and can't see it right away, is there something else you can do? Yes, you can perform what's called a substitution, which simplifies the calculations so you can see it better. Once you become good at it, you can skip that step and just visualize it in your head.
But let's show how to write it down if you need to practice.
So I'll take example 4 once more, but now I'll solve it with a method called integration by substitution. So example 4 again. Same exercise. So it was the integral of sine squared of x times 6x. And over here on the right, I'll start a thought box. There's the corner of a box, and shortly there'll be another corner that finishes the box down here. Once I know how big the box needs to be, I'll finish it. I don't know that yet. It depends on how small I write.
Inside that box, I'll jot down some thoughts.
And I find these thoughts like this. I ask, is there family? Because x squared differentiated gives approximately 6x. Okay, that's the first thing I discover. So I think the app that differentiates roughly changes the other. I'll call it something new. I'll call it t. And calling something ugly beautiful, that's called a substitution. You replace something ugly with something beautiful. So the ugly x squared there, I replace with a beautiful t. I've simplified the way of writing x squared. I'll just call it a c instead. That's the first step. I'll show it a couple of times so you can learn the procedures. So I think, what do I get if I differentiate t with respect to x? You write it like this. Now I differentiate t with respect to x. And differentiating x squared with respect to x, that gives 2x. So I think, okay, I'd like to know what dt becomes, and there's a good reason I'd like to know what dt becomes. It's because I'd like an integral where I don't write dx, but dt. So I beautify the integral by changing variables, and that process is called substitution, which means replacing. So in principle, I replace x squared with t, and I end up replacing my dx with a dt. But it must be done correctly. Look here. If I just multiply dx over to the other side, then it says here that
dt equals 2x times dx.
So if I had 2x times dx, I could just call it dt, but I don't have that.
2x times dx, I have 6x times dx.
So my brain thinks, darn it, I don't want 2x dx, I want 6 dx. So I just multiply by 3 on the right side of the equality sign. So I multiply by 3 over here and get 3t. I'm equal to 6 dx. Look, now I'm working on 3 different projects, and now my notebook is out of pages, so now I can wrap things up. What I can see now is that if I insist that x squared should be called t, then there's t there, because x squared was t. And I've shown you now that instead of 6x dx, you can just as well write 3 dt. So here, I write 3 dt. And it's the same thing. 3 dt is another way of writing 6x dx. So I can actually write my integral in a new way, which looks like this. The integral of sine of something beautiful, namely c. And instead of writing 6x dx, you definitely shouldn't do that. You shouldn't mix t and x's. You can't be in 2 universes that have nothing to do with each other at the same time. You can't. You're either in x land or you're in t land. And there are some mathematicians who mix it and like being schizophrenic and being in 2 different universes at the same time. I don't recommend doing that. Instead of writing 6x dx, I just write 3 dt. And now you can see that I've transformed my integral into a completely different universe. And what that means is that now I'm not integrating with respect to x, now I'm integrating with respect to t.
And this integral is much easier to solve than the original one. Because that threshold is a constant, you can just put it aside.
Hold it. Napire. Oh.
Outside, right? So this can be written as 3 times the integral of sine of d dt.
And how easy is it to...
It just says, can't you find me an antiderivative of sine of d with respect to t? Yes, that's minus cosine of t.
And remember to multiply by 3. So this gives us
3 times minus cosine of t.
Suddenly, it's a constant. So now I've actually solved my integral over in t land. Then I just switch back to x land, because what was that t again? All right, t was x squared. So I just plug in x squared there, and then I'm done. So I have answered the original question. So I'll just finish writing this, then I'll write the question, giving 3 times minus cognos.
for x, preferably. And then it's finished.
And the method I've shown here, where you do some calculations off to the side, can be a good idea to start with until you get really good at handling the bending equations in your head. And later, you can skip that. What does Ash say? Yes, that's what I usually do. Yes. And it's not an annotation I came up with. It comes from a really good authoritative source, namely Niels Bohr's brother. His name is Harold Bohr, and he wrote, in my opinion, the 4 best mathematics books in Denmark. Mathematical Analysis, B14. But you can't buy them new anymore. You have to find them in a second-hand bookstore.
That's where I found mine.
But they are amazingly good, and they are written so well. It's incredible. And they were written by 3 authors, and I have a handwritten edition, which was printed, so I obviously don't have the original, but I have a printed copy of their handwritten edition, and you can't tell when it's Harold Bohr, or Mollerup, or Anderson writing, because they all learned to write the same beautiful cursive, and it was drilled into them with a cane, I imagine. They all write the same. It's just incredible. But I can recommend them anyway, and that notation I remember borrowing it once when I was reading their Mathematical Analysis B2, which deals with integral calculus. Super thorough.
Are there any questions?
It disappears.
You're
Because
asking
you're on that topic and you're answering that.
So let's just see what we're asking about. Can you find a function such that when you differentiate it, it becomes f acting on g times g self-differentiated? That's what we're asking. Yes, it's an antiderivative acting on g. That's the answer. Why? Because when you need to differentiate an antiderivative acting on g, you first differentiate the outer part. That gives a little f, and let it act on g, untouched. And finally, you multiply by g self-differentiated. And that's exactly what it says there.
This differentiated gives that. Therefore, the equality sign is true.
And what does that mean? It means that here is a function, which if you differentiate it, gives that. And if you then look at the example, is the equality sign true as well? Hopefully. What does it mean if it's true? That if you differentiate this with respect to x, you get sine of x squared times 2x. Let's try. Minus cosine of something differentiated. That gives sine of the same something as before, meaning sine of x squared. Bang. Remember, then they're working with the inner function, differentiated, and the inner function is x squared, and x squared differentiated gives 2x. Ah, that was there too. So everything checks out. Help? Yes.
Any other questions?
You may have had a math teacher who insisted that you should isolate dx down here instead of dita. Forget it. It's a terrible way to do it. It's always smartest to isolate the differential if you ask me. But some people have a different opinion. And there's room for a little emotion in math. But not many feel there's space for that. So here's a bit of room for emotions. But I recommend doing it this way. I find I make fewer mistakes when I do it this way. Okay, let's try example 5.
Can I get shot? Can you take a picture?
Maybe some people wonder, why should we learn this hand calculation when I've just shoved it into the software? And there's a tendency that today's high schools teach in such a way that one simply learns to plug it into a program and then the answer comes out. And then in the end, you have a good student who's great at software, but not so good at math. So that's why. It's because part of learning math is the craftsmanship. Your fingers need to know it, because if they don't, you can't use it out in the field when you're working as an engineer, making assessments. What are you going to say? Hang on, I need some software. How many equations do we need? Wait, I need some software.
Give him an assessment now. So you need to learn some level of hand calculation.
You don't learn it as thoroughly as people did in the old days. And I can also see that if I go back and try to solve final exams from way back, I come across problems I can't solve. This just goes far back in time. Surely I'll find some I can't solve.
Sometimes one can feel a bit humbled when teaching this stuff if you can't solve them.
Because if I go way back, for example, if 1945, and solve high school tasks, there's some tasks that are so wild, where it states, of course, you must solve them. And some tasks are really intense.
Where I
it
prove
states
that it's a well-founded and orderly
you must
algorithm.
solve them.
Or something like that. I don't even know what kind of algorithm it is.
So it was something they learned back then. Because they didn't have calculators, you had to be able to do it. And we skip that today. So everything you can't calculate by hand, without knowing some very special, totally bizarre technique, we've started to drop.
But we insist that you should still be able to do
The
one
best
step
is
with manual
also to
calculation.
understand what's going on.
So just think, yes, bring it on. Don't think, oh, I don't know, because it can be entered into Mabel. It's a quick way to become dumb, just learning to input into Mabel. Some people type the equation 2x equals 4 into Mabel and solve it there. Should we know what x should be multiplied by? What happens when you multiply?
2 men from 4
It's
sets.
solve that,
That's
right?
right. That's right.
We can see it too. For example, on D2.
We're receiving applications from students who got a 12 in math. You can see what their grade was when they applied, and then we give them a test, solve these problems by hand, and many of those who got a 12 score less than 0.2 on these hand-calculated tasks. That's a bit scary.
And it's because they've relied too much on software or calculators. So we hardly use those in these courses. We just want you to think first.
Let's take another example. What example was I at, number 5?
Here's an example from 1998. The final exam I took back in 1998. I still remember that problem because I was puzzled by it. Partly because I started teaching at 30. Then I recalled that problem and
As
used
an
it.
example since then, it looked like this.
E to the power of square root of x, all divided by the square root of x.
Just solve that integral quickly.
Wow. I remember when I saw that, I thought, what?
What kind of weird integral is that? And luckily, I realized that there was a hidden one there. And then I could write it like this. And then I realized it was substitution. And I thought, oh, is there family? If you differentiate the square, what do you get?
You get 1 over 2 times the square of x, and that's about what's here.
And remember what the word about means. When is some factor something I can just do creative accounting with? So I would have liked to have a total down here, because if there was a total down here, they would pretty much have given me the answer. So you do the cheeky thing to just write a total down here, and then you ask yourself, what's the cost of writing a total there? Well, it costs me to also write 1 here, where 2 goes out with 2. And of course, it still says times 1, because 1 is the ultimate neutral operator, not multiplication. So that total, I just get from the integral.
So with creative accounting, I get this.
And now it's all set up perfectly. Who is F? Who is G? And who is G naught? This guy here, that's F.
And who does he affect? Her. So that's G.
If you differentiate her, who do you get? This guy? This gives the note. Are you following along with that? So what does it say? I need to find big F and let it act on G untouched. Then I'm done. What's the antiderivative of E something? It's E something.
E, what is it? The same thing as before. So the answer is
To the power of x squared plus g, and then we're done.
Whoa. Oh, that was strange. I totally forgot there were 2 variables involved, and 2 survives.
thanks. Thank you so much.
Never calculate in public. That can be hard to maintain if you have to teach mathematics and you're not supposed to calculate in public. But yeah, of course, I need to work with the 2. I just forgot I have 2 variables up here. If that equation is true, then I should be able to differentiate that one, and then I should be able to get that up there. Let's just try it. Let's just do a little careful check that you don't show at an exam, but just on a piece of paper, just to see if you're right. So I'll just differentiate that right now. That's another way of saying I'm differentiating it now. 2 times the squared x, and I can forget all about k, because I know it disappears when I differentiate. So the important thing is, if what's differentiated gives that fraction. So let's try it. 2 is multiplied, so it will remain. E differentiated becomes itself. But it's a composite function, so I need to remember to multiply with something self-differentiated. And the derivative of the square root of x gives 1 over 2 square root of x. When I both multiply and divide by 2, they cancel out. And I have to multiply e squared x in the numerator. So this gives e squared x over squared x. That's correct. So I trust your equal sign. But there needs to be a picture. I have to be the first to admit that I don't solve it that quickly. I was sitting and canceling something with it. That's why I can still remember it.
And I thought, what the heck were they thinking with this problem here, man?
Ouch. Back then, it was really hard to get top grades because you got 11 if you had 97 points or more. And you also got 11 if you had 100 points, unless you did something that shocked the censor and examiner with its brilliance.
Then you still got 11.
Today you get 12 with 92 points.
It's a Thursday.
So it has gotten harder. It has gotten harder. Or it was harder than it has become. It was harder for the old 11 than it is for the current 12. But we had to. Because the Americans invented a grading scale that was kind of lame. So we had to copy it. Now I'm writing a lot of assignments in integrals. And I'll start with some that are nice and easy. And then gradually they'll get a bit harder.
Could they just pause the recording?
So I'll write everything down, and then we can start recording again, briefly, so everyone can see the assignments. And then you just start solving them as I write them. And right here, I'll say, here are some of the assignments, and then you
Pause
can
it
just,
again.
all right, that's fine. So go ahead and solve them, and let me know if you need a hint or a bit of help. Some of them are a bit harder. You might need some help with those.
And with this one, I think almost everyone will need a
Is
bit of help.
anyone being creative?
If you feel like you're just on the edge, you don't have to raise your hand or anything. I'll walk around and help out. And try to help each other a bit.
All right, the camera's rolling again. And done. We'll just clean up under here.
We're on the board before we stop for today. So we'll save the complex numbers for next time. But I have a favor to ask if you could read the tasks aloud.
To me, task 1.
Has anyone else written them down? You've noted them? Great. Lund, you just take this one. Okay. First task. We need to find the integral of x squared plus x cubed.
And plus x to the 4th.
And there we use that we can integrate term by term. So I integrate this, that, and that separately. The integral of x squared must be 1/3 x cubed, because I need to increase the exponent by 1. And remember to divide by the new exponent. The integral of x cubed must be 1/4 x to the 4th, because I need to increase the exponent by 1. And remember to divide by the new exponent. And likewise, the last term must be 1/5 x to the 5th. And finally, we can remember to add the constant to get all the antiderivatives. So that's the answer to task 1. And this is why I also like boards. You can make dotted lines. Exercise 2. It states that the integral of x to the 4th power plus a constant times x to the 5th minus 30, which goes to 30. So just like before, I have to integrate each term separately. So I integrate this, and this one separately. When I integrate the first term here, it simply gives 1/5 x to the 5th. Because I raised the exponent by 1, and remember to divide by the new exponent. Here, I let the 1/2 stay first, because it is the constant that is multiplied. And constants that are multiplied stay during integration. So now I have to integrate x to the 5th. And it results in 1/6 x to the 6th. Now I can multiply 1/2 and 1/6 and get 1/12 in the next line when I write it out neatly. Here, there's a minus and 1/3 of e's. And x to the 3rd integrated gives 1/4 x to the 4th. And then plus our famous constant, which we must not forget. And then I can just write it neatly so that it says 1/5 x to the 5th plus 1/12 x to the 6th and minus 1/12 x to the power. And then plus k.
So that's the answer to problem 2.
Problem 3. It says the integral of x to the power of minus 3 minus x to the power of minus 4. Fancy antiques. Again, when I integrate term by term, I integrate each part on its own. X raised to the power of minus 3, integrated. I need to add 1 to the exponent, so I get x to the power of minus 2. So that's my new exponent, minus 2. That's my new exponent. And then I have to remember to say that 1 divides by the new exponent in front. So that apparently gives minus 1 hat x to the power of minus 2 when I first integrate it. That minus is what I initially stood with. And then I add x to the power of minus 4. X to the power of minus 4 integrated. I need to add 1 up there. So it gives x to the power of minus 3. But I have to remember to say that you divide by the new exponent, which is minus 3 here. And finally, I have to say plus k. I can then rewrite it a bit. So here it really sees minus 1/2 x to the power of minus 2. And here it says minus minus, which is plus 1/3 x to the power of minus 3. And then suddenly, and that was exercise 3.
Any questions? Exercise 4.
In exercise 4, it says that the integral is 5x cos theta.
Dix.
5 theta is a constant, so it stays on
The
stamps.
function for cosine is sin. So it must give 5 times sine of x.
Okay, and 5. It looks a bit like, it says the integral of 7 times sine of x to x. And again, dx is part of the question, so you shouldn't wonder where dx goes. Dx disappears when you answer, because dx was part of the question. So I need to find all the antiderivatives of 7x sine of x. Well, I guess I must do that. The 7 stays, and the antiderivative of sine is minus cosine. And I might as well put the minus in front.
Overlying and plus k.
Flat rate 5.
Exercise 6, where it says that the integral of the square root x equals x.
But we learned in algebra that taking the square root of something is the same as raising that something to the power of 1/2. So this can be rewritten as x raised to the power of 1/2. And now I can integrate it. I just need to add 1 to the exponent. If I add 1 to 1/2, I get 1.5, and I need 3.5. So it becomes x raised to the power of 3.5. If I remember to say 1 divided by the new exponent down here in front, and then plus k.
1 over 3.5.
That's the same as the reciprocal of 3/2. So it gives 2/3. Because 1 over a fraction is that fraction flipped upside down. So I just flip the fraction here upside down. So I get 2/3. X raised to 3/2. That was funny. And that was the answer to problem 6. Now it gets a bit harder. And now we move on to problem 7. And I can just add a bit of spice. And just gather an archive. Problem 7 is determine the integral of x squared times e to the power x. Here we have two functions multiplied together that are not in the same family. So there's no differentiation family between x squared and e to the power x. So you can't use substitution. And that's why you use partial integration. That's what it's called. Partial means partly, because when you use rule number 3, you're only partly done after using the rule once, as a new integral appears that needs solving. That's the name partial integration. So we have to decide which one is f and which one is g. And you have to think about which of these two functions becomes nicer when differentiated. Where nicer means easier to deal with, if you have to integrate something that's multiplied with it. And there we see that x squared differentiated gives 2x, while e to the x differentiated gives e to the x again. So this one gets prettier when differentiated. So I choose to call this one f, and this one I choose to call y.
I call it g. And the reason for that is because soon we'll be
If you write the rules, we'll see that what gets differentiated is what's being differentiated.
Goes when you use the rule. That's why it is.
That one should be called g, because it gets nicer when you differentiate it. And the rule says, find the antiderivative of f and multiply it by g, untouched. Then write a minus and a new integral sign, and take the antiderivative of f and multiply it by g differentiated. Then this rule here is partial integration. That is partial integration. Because then a new integral pops up, which also has to be solved. So once you've tried the rule once, you're only partially done. So there we get, now you can see why it's g we're looking for. Because it's g that's being differentiated, and you want this integral to be easier to handle than the integral. Otherwise, you're going backwards. So first I find the antiderivative of e raised to x, which is e raised to x. Now I should start with g prime, but I wasn't going to say that yet. So I need to write a minus for the new integral sign. Then again, I need the antiderivative of e raised to x, which is e raised to x. And I need to multiply by g differentiated, but that gives 2x, because x squared differentiated gives 2x. And now we see that we're not done. A new integral has appeared, which also needs to be solved. So what do we get when we solve this? Well, we just use the rule here written. So we use the rule inside the rule. And in task 8, one has to use the rule inside the rule inside the rule. But let's just keep calculating. This is done. I can't do anything more with this. So I'll copy paste it by writing it off from the board, like that. And then I'll just write a parenthesis here, because when I need to calculate this, I can see that there are two terms. So it's important to start with a parenthesis. Now, who should be f? Who should be g? Again, this one should be g, and that one should be f, because two x's look better when differentiated. So I find the antiderivative of e raised to x, which is e raised to x,
Multiply by g prime, which means multiply by 2x.
minus a new integral. That's why it's called partial integration. But I'm still not done. And the new integral has to be e raised to x, which is f.
Multiply by 2x.
When you differentiate it, it gives 2, and then it's x. And now you can see why this parenthesis is important. If I hadn't placed it, I would have made sign errors. And you clear a minus parenthesis by applying the sign to every term inside the parenthesis. So we can continue calculating with it. This is done. So I'm copy pasting it for myself and to x squared. And then I clear the minus parenthesis. So I get minus x times 2x. And finally, I just need to solve this integral here. But it'll end up with a plus now, because minus times minus is plus. And the antiderivative of 2e to the x is 2e to the x.
And then plus the famous constant.
And now you can see that e to the x appears here, here, and here. It's a common factor, so I'll place it outside the parentheses and get x squared minus 2x plus 2.
End parentheses plus k. And that's our final result here. Here are all the antiderivatives of the integrand. And that was experience 7.
Now we just need a sponge. Stagger piece, can you grab it?
I don't really like doing it by hand. Does anyone have a C1?
Does anyone have a comms t-shirt on? Oh no. Just in the next room, Rune. There's a sponge in there. Could you get it?
So I'm waiting here to see if anyone has any questions in the meantime. You had the chance to be a darling too, just like Aska.
Does anyone have questions about it? You can see that you need to stay focused. But something that helps is writing right under each other. And then calculate it, making it nicer each time. That way, you won't lose track. Just that easy.
I'm right here. There's no sponge.
Or is it right in? Or is there a toilet in between? I can speak to that. It gets me looking at the toilet. I can inform you that it hasn't gone. Okay, let's look at task 8. Wow, it's so easy to erase.
You can tell I'm talking to the management at Absolute in these videos, yeah?
When I was hired, I was told that chalkboards were a no-go. And it couldn't be discussed because it was the policy that they weren't used. But we do it now.
All right, so task 8.
We have an integral called x cubed times e to the x.
And it's actually just
as
like...
easy or difficult as the other one. You just need to take one more step, because again, I need to use this rule here. Capital F times g minus the integral of capital F times derivative of g.
And then you just get started.
And we call this one f, because x cubed becomes 3x squared when you differentiate. And 3x squared is considered nicer than x cubed because the exponent is smaller. And then we know the next time it'll be even smaller, and next time it'll be even smaller, and then we're done. So we get the antiderivative of e to the power of x, which is e to the power of x, times the other untouched part, which was x cubed, minus an integral of e to the power of x, times the derivative of that, which gives 3x squared. So that was stubborn. So we keep going through the day. That one's calculated, so I'll just copy it from myself. And here I can see that 3 can be factored out of the integral, and now I have something to calculate that has multiple terms, so I put it in parentheses. And what I need to calculate is the integral of e to the power of x times x squared. So I should just write that. E to the x squared, dx.
But we've already calculated this integral.
We calculated it just before, so no need to do it again. We'll just grab the result from earlier. So that gives e to the x times x cubed minus 3 times something, and that something was what we got before. I don't know if any of you were smart and wrote it down, but didn't it give something with e to the x times the second degree polynomial here? What was written here? Don't say anything else. Minus 2x or something like that.
Minus 2x plus 2 minus 2x. And then we need to remember to write plus k at the end.
I assume that's right. I just can't remember what I got. Is that correct? And then we can sort of finish calculating, because now we can see it says e to the power of x cubed. And here it says minus 3e to the power of x squared plus 6xe to the power of x minus 6e to the power of x. So in principle, it can be expressed as e to the power of x times some third degree polynomial. Let's see if I can figure it out. You get x cubed from here. And here I got minus 3x squared. And let's see what I have as x. I have plus 6x.
And then I have minus 6.
And then plus k.
So here we have the result.
That was probably the hardest one I've come up with. Let's try problem 9. In problem 9, it says the integral is sine x to the 5th times 5x to the 4th. That clattering is driving me a bit crazy too. But that's why we wanted those boards that could move up and down. Here we discover there's a family, because if you differentiate x to the 5th, you get precisely 5x to the 4th. Not even just approximately. You get exactly 5x to the 4th. So if you want to do the substitution, you can just write it out here. I set t to be the inner function x to the 5th.
So I differentiate t with respect to x
and get 5x to the 4th.
And then I multiply the x over to the other side of the equation and isolate dt. It then becomes 5x to the 4th. Multiply by dx. And then I stop the thought process, because now I can see that 5x to the 4th is 5x to the 4th.
bx. That's exactly what it says here.
So that means, in disguise just .dt, there's a t. And in here, it's t. So that means my integral will look like this. The integral is sine of t dt. If I just pull this a bit further away, I can avoid that mess there, I hope. And then I just need to find the cofunction of sine of something. The cofunction of sine of something is minus cosine of that something, plus constant of integration. And then we do substitution in reverse, placing it in t's position, as t is now defined as x to the 5th. So I get minus cosine of x to the 5th plus cog. And that was exercise 9. Oh. It's almost time. You have about a minute left, so I'll just cover problem 14. And if anyone has questions about the others, I'll be happy to take them after I've stopped the camera you can come up and ask. Otherwise, we'll start with the last ones next time. But I'll quickly tackle problem 14 as the last thing for today, and next time we'll begin with the curriculum. You're in for a treat because it's one of the coolest topics. It's one of the coolest topics in mathematics. I know the complex number. It's just so exciting. It's like a whole new world. Our understanding of numbers suddenly gets an extra dimension next time. It's magical. It's actually psychedelic. There's an extra dimension coming. So, problem 14.
It says the integral is 2x plus 3 divided by x squared plus 3x. And then plus 5.
It's MC God here. Made that up. And what you are supposed to notice in this problem is that the denominator differentiates the numerator.
Not just approximately,
but right
because
now,
if you differentiate x in fx, it's not
2
simply
plus
an
3x plus 5. What's the result? Yes, x squared differentiated gives 2x. 3x differentiated gives 3. 5 differentiated gives 0. So I can see I could call the whole denominator t, because the whole denominator differentiated gives the numerator. And if you do that, some magic happens. Let's try setting t equal to x squared.
Plus 3x plus 5.
Again, start by differentiating t with respect to x.
It's called dt over dx.
And that gives 2x plus 3. So I just multiply dx over to the other side of the equation
And get a dt equals parenthesis 2x plus 3.
Can't it? The reason I should put a parenthesis is because dx has to multiply both terms, right? Why isn't the parenthesis important here? It's because dx is multiplied by the fraction. If you put dx up there, the parenthesis would become important.
So we can see that 2x plus 3 dx is exactly what's written here.
So inside that bubble, it actually says dt because it's 2x plus 3 times dx. So I'll just replace the bubble with dt. And the whole denominator, what was it again? Oh yes, it was the thing I came up with calling t. So it actually just says that t over t. I had made an institution, and it can be rewritten as the integral of 1 over t times dt. Why call it that? Because you multiply a number on a fraction each time at the top, and 1 times dt is dt itself.
So that's why I can also do this and pull the t down in front.
And then I need to try to find a function that, if differentiated, gives 1 over something. That's ln. See, that's something, but you can only take len of something if something is. Therefore, you need to put a numeric sign around it. So you ensure you're not taking an internet negative, and then plus k. And now I can do a backward substitute and put x squared plus 3x plus 5 in where t goes. So dn of the numerical value is x squared plus 3x plus 5.
I'll take an end. Plus OK.
And 2 lines underneath.
And with that, I want to say thank you for today. See you next time.